The introduction and the opportunity to present something about scanning probe microscopy applied to photovoltaic materials. So I'll start again with a question: who has done scanning tunneling microscopy? Okay, quite a few. What about atomic force microscopy? Should be more. Good. I will start very basic, actually, with the instruments and introduction to the different working modes. Maybe a bit different from the design of the other presentations. But first, since the INL, International Iberian Nanotechnology Laboratory, is a fairly recent organization, I wanted to introduce a little bit the place. So it was kind of conceptualized, created in 2005 as a decision between the Portuguese and Spanish governments to establish a research and development institution. And in 2008 there was the headquarters agreement which established INL as an intergovernmental organization. So we have a similar status as CERN, an international organization. And operations more or less started in the beginning of 2011. Then this building started to be populated. And after a few years, with a very slow increase, over the last 5 years, we have increased quite a lot in number of people. So now I looked these numbers up 2 days ago. We are 370 people, out of which 311 researchers and 35 nationalities. And Braga is in Portugal, as you already saw before. It's in the very northern part. Don't get confused, the weather is not so nice as you would expect. And in the winter it's a lot of rain, it's dominated by the Atlantic Ocean. So I think the French people can compare to this part of the country. So we have similar weather than that, but in the summer it's nice. So INL is very interdisciplinary. We do a lot of different things, which is on one hand nice. On the other hand, it's sometimes a challenge because we are always only a few people working on the topics. So we have research on food, going with food packaging, food safety, food authenticity. There's groups working on environment, doing water monitoring, water purification, nanotoxicity. Then we have several groups working in health, in diagnostics and therapeutics. All of this is always involving some kind of nanotechnology. So then we have energy, mostly renewable energy, photovoltaics, which is my group. But we also, in other groups, we work on hydrogen technology, batteries, supercapacitors. So everything in principle that you need to have a renewable energy system. Then there's lots of people working ICT, advanced sensors. We have a very strong effort on magnetic tunnel junctions, which are used in many different applications as sensors. Nanoelectronics and photonics, and then also future and emerging technologies. And there we put everything that we don't know yet what application it will be for. So there's a lot of 2D materials there, but also other materials. Novel instrumentations, so when we develop some method that can be applied to very different things. And then more recently we also started working quite intensely on quantum materials, science and technology. So in terms of infrastructure, we have one building. Well, actually we have two buildings. One is a social building where we have some guest rooms for people that visit, and a nursery and some gym classes. And then the main building is here, this part. We have an auditorium. We have a big clean room for micro and nano fabrication. And there's a 200 millimeter wafer process line, so we can actually work quite well there. And actually it's not a CMOS clean room, so it's not electronic grade silicon that is fabricated there, but they allow all kinds of other things. So the magnetic materials are there. Also we can go in there with our solar cell materials, so they allow copper and gold to be inside the clean room, which is very convenient for us, of course. Then we have a high accuracy suite, which is 2 levels below ground, directly with a concrete block onto the rock. So the vibrational situation is very good there, and this is also where our scanning probe microscopes are located, and also our electron microscopes. So this is this part. And there's a central biolab, and then here is it's a wing with 2 times 10 labs and offices and open space for all the people doing the research, and we have 2 floors of those. So in the bottom floor we have dry labs, and in the top floor we have wet labs, more for chemistry and biology. So with this, I go to the topic of the presentation, scanning probe microscopy. First, most of my examples will be on chalcopyrite materials. We saw yesterday a nice introduction to the materials, so you know all of this already. Just a quick reminder, record efficiency at the moment, 23.35. By varying indium, gallium, or sulfur and selenium composition, we can vary the band gap between 1 and 2.4, which includes the visible spectrum, so it's very suitable materials for solar cell applications. Also because it's very short absorption length, so we need only a thin layer to absorb all the light. And a typical solar cell consists of 5 different polycrystalline material and with different thicknesses. So we have molybdenum as a back contact, then we have the absorber layer, typically about 2 microns thick, a buffer layer, cadmium sulfide, and a zinc oxide window layer, which is actually a double layer here. And then at the interfaces, there are sometimes other materials that develop, for example, molybdenum selenide. We also heard this yesterday, I think. So what will become important later for the examples is that it's polycrystalline. So you can see here, this is not as nice as what Andrea was showing yesterday with the 3,5 materials, but this is it's crappy stuff. So scanning probe microscopy, I already asked you if you know these. So I will start very basic. So I hope you don't get too bored if you know all of this already. But it's a good reminder, let's say. So this was developed by Gerd Binnig and Heinrich Rohrer in '82 at the IBM Research Laboratories in Rüschlikon in Switzerland. And only 4 years later, they already got the Nobel Prize for this. This is a quite short time to Nobel Prize, so we can all still have hopes. We are all still young enough. And I read on the plaque outside, there's 44 Nobel Prize winners that have been here as students or lecturers, so even the lecturers still have a chance. And there was well, the only photoelectric effect, of course, yeah, but other than that, there was no PV Nobel Prize yet, right? So. So scanning tunneling microscopy. This is the first images published by these 2 guys. And if you look at this, it's quite difficult to understand. And actually, if you think yourself back there, if you are able to think yourself back there, so the younger ones maybe not, this is slices of paper that they put together. So this was done by a plotter scanning a line. And then they stuck this together so they could see this kind of 3-dimensional impression here. So it was actually not easy to identify what they were actually measuring. So how does it work? We are visualizing the atomic structure in real space, and this was the first time this was actually possible to do that with the scanning tunneling microscope. And what we do is we use a very sharp tip, atomically sharp ideally, and we scan it across the surface. So it's similar in some sense to a record player. Again, this goes back to maybe before the lifetime of some of the people in the audience. And we keep the tip at a specific distance to the surface and thereby scan the surface morphology. And this is done employing a quantum mechanical effect, which is the tunneling effect. So if you have your sample and your tip, and then in classical physics, the electrons from the sample, they could never cross this vacuum barrier here. However, in quantum physics, the particle, the electron, has a wave character, and there's an exponential decay of the wave function of the electron that reaches out of the sample and can, if the tip is close enough, actually enter into the tip. And then that means there's a finite probability to reach the other side of the thin barrier. So the observable, which would be then the presence of the electron in the tip, is related to the square of the wave function. So if we have the wave function that decays outside of the material exponentially, and here in this kappa we enter the barrier, so it's the barrier height, and then of course the d is the barrier width, so it's the tip sample distance. And this is the kappa, which includes essentially the barrier height here. So if the d is close enough, there's a finite probability to have the electron tunneling into the tip. So if we square this, then we get this exponential behavior for the current, which is the one we want to measure. So it's scanning tunneling microscopy, and we measure the current. So it's very this exponential behavior is very important because it determines essentially the resolution. So if you look at the numbers a little bit, then you realize that the current changes by a factor of 10 for every angstrom in change of distance. So you're very sensitive to the distance here. And that at the same time means if most of the current is going through your last atom. So if this atom is only 1 angstrom behind this one, further away from the sample, then this one only contributes 10% of the current to the whole thing. So we get very sensitive to the foremost atom on the tip. On the other hand, normally people say easily, oh, we measure the surface topography or surface morphology. But this is not completely true because actually we are measuring currents. So the currents have to go, of course, into some electronic states. So we're measuring actually a surface morphology or topography of the density of electronic states. And this is in some cases very important because, for example, here we have a density of states corresponding to the atoms, but you can imagine surface structures where some of these electron lobes would not stick out of the surface, and then those atoms would, of course, not be as visible. So how is it built? So this is a typical block diagram, very simplified, of a scanning tunneling microscope. We have the tip, of course, we have the sample. Then we need to scan the sample very precisely. So for this we use a piezo scanner, and I will explain all of these elements in the following slides. Then what we need is a current voltage converter, so to look at the current that comes from between sample and tip. We have a controller that controls this current to be constant, and that at the same time gives our tip height signal, which we feed into a high voltage amplifier to apply to the piezos. And on the other hand, we have a computer that records all our signals and controls the scanning. So for the tip, initially people used just a wire cutter and a platinum iridium wire, platinum iridium because it doesn't oxidize easily. So you can do this outside or in air and then go to your vacuum system. Normally scanning tunneling microscopy is done in vacuum, ultra-high vacuum. But your tip doesn't look really nicely. So what's mostly done is actually electrochemical etching a tungsten wire. So you have a KOH solution here, a ring electrode, and then you have a wire in a controlled way inside this ring. You apply a voltage between your wire and the ring electrode, and then you have electrochemical etching right at the surface of the liquid. And this etches your tip until you get the meniscus where it just drops off. So this is the current as a function of time, and at some point just the wire, the bottom part drops off, and then you pull out and you remain with a very sharp tip. And this one you can still prepare a little bit further inside the ultra-high vacuum system to get it even better. So the next thing is the next ingredient is the piezo. Piezoelectric elements or materials, they are characterized by having a different center for positive and negative charges. So they, in the crystal structure, they don't coincide. So as a result of this, you can either apply a bias, and then you get a mechanical deformation of the material. So this is what we use. Or the other way around, you can apply pressure to your material, and then you get a voltage. But here we use the deformation as a function of applying a voltage. And typical materials are quartz, and then what's mostly used is lead zirconium titanate. And these piezoelectric elements, they can be designed in different ways. So a very simple one is a tripod here. Most commonly used one is the tube scanner. So you have actually a ring, a cylinder of this piezoelectric material, and then you have an electrode on the inside, and you have patterned electrodes on the outside. So depending on how you apply voltage to the Z, the Y, and the X, your tube starts deforming in a specific direction, or if you apply the same voltage to Z and X, then actually you can move the tip forwards and backwards. So with this one you can get all three directions in this design, of course with this one as well. And then another typical form that is used in a lot of homemade systems is a beetle type. So you have You have the tube here. This is for fine scanning the tip. But then to approach it, because you need to, of course, you cannot look at how far you are from the surface at this dimensions. So you do this optically. You bring this very close. And then you apply a stick and slip motion to bring this whole tip down these ramps here into close proximity. So this, we are talking a few angstroms distance, so that you can actually get a tunneling current appearing between the sample and the tip. So this is more the type for the coarse motion. And this we had already. So there's different operation modes. So one thing is, one possible way to apply this is the constant current mode. I said this essentially already. Here you just always keep the tip at the distance where it gives the same current, some nanoamps or whatever. And then you do a feedback loop to apply the Z voltage to the Z piezo, so that the tip is maintained constant above the surface. So you essentially get a direct measurement of the surface topography if you have a calibration of your voltage, the Z voltage. So that's a very simple and very common one. But it requires a feedback. And there's another way to do this, is to use constant height mode. So here you're actually keeping the tip always at the same height. And then you're measuring the current. So if you're here on the lower step, you have a lower current. On the higher step, you have a higher current. This is much faster because you don't need to do the feedback. So you don't have a controller to do the feedback. But you only get relative information. So you cannot really know how high your step is actually. So this again, this image, so this I mentioned already, this was quite difficult to measure. So modern times we have computers, so everything is computer controlled, and we get these images much nicer. And this actually was the image that helped to finally decide what is the silicon 111. So we just learned what the round brackets mean. It's a plane, and then there's different reconstructions of these surface planes. So this one is a 7x7 reconstruction, which was known before, but it was not really decided yet how the structure looks. And this STM actually helped then to identify how does the structure look. And there's a lot of atoms in this surface plane. And what we see in STM as these spheres here are actually the atoms here. So only these atoms we see, and the other ones are slightly behind the surface. They are usually not visible here, and then you have these corner holes where there's atoms missing. So it's a very complex structure, but it's a model structure. So wherever surface science is done, the 7x7 silicon 111 surface it's a very famous surface. Questions so far? Good. We continue. Atomic force microscopy. So one of the big disadvantages of STM is that you need actually a conductive sample because you're measuring a current. So if your sample is not conductive, you're stuck. You cannot use the scanning tunneling microscope. And therefore, Gerd Binnig and Cal Quaid and Christoph Gerber, they developed the atomic force microscope. And this is a paper from '86. It received more than 10,000 citations, so it's a very common technique. You probably heard this many times already. Atomic force microscopy is now, both of these microscopies enabled nanotechnology to some extent. So they wanted to also measure insulating surfaces, and then what they did, they built a system that has a cantilever with a sharp tip here, and then on the back side of this, I think it was an aluminum foil. Yes, it was a gold foil here with a diamond tip. And then on the back side of this lever, they put an STM. So essentially, they transferred whatever was mechanically scanned to an STM. Very complicated in some sense, and nowadays it's much easier. And they were already foreseeing that you can measure interatomic forces with this, even though at that time they probably didn't. So this is how it looked, very complicated, very home built, and I think one of these guys is in the Technical Museum in Munich. So you can actually take a look there by yourself how it looks. And the STM is somewhere there. I tried several times to identify exactly where it is, and I don't manage. So this also tells you what, however crappy your thing you do in the lab looks, it might still be very valuable. Okay, so nowadays things look a lot more professional. We have now 25 years or more of AFM, no, 35 years. So nowadays you use actually silicon cantilevers, which with a very well-formed, nicely shaped tip. So this is all done by micro machining in clean rooms. So these tips are very sharp. They have a tip radius of 20 nanometers or even less sometimes. And what governs the interaction between the sample and the tip is this force distance curve. So if you go very close, so let's start here. If you're far away with your tip from the sample, there's of course no interaction. Now you get closer and closer, then at some point the van der Waals forces, they become important. These are attractive forces between tip and sample atoms. And at some point, if you go too close, you get a lot of attractive forces, but then it converts into repulsive forces. So that's when you go very close and you get essentially a Pauli repulsion between the electron clouds of the tip and the sample atoms. And this part of the curve here is you can model this by the or approximate this by the Lennard-Jones Potential, which is a phenomenological way to describe these forces. And instead of using a STM on the backside of the cantilever, nowadays what's most common is to use a laser. So you shine a laser to the backside of the cantilever, which is reflected to a position-sensitive photodiode. So these are kind of four small photodiodes, a four-quadrant photodiode to measure how the beam is deflected on the backside. And of course, you know this very well, a small movement here makes a big movement over there, so you're very sensitive to small movements of the tip with this. But there's also other detection modes. We saw this one already. This is the beam deflection. There's interferometry. You can do you can do capacitance, you can do piezoresistance or piezoelectric. And actually, more recently, there's the piezoelectric one is becoming quite popular because you don't need an optical system and you can get very high precision measurements. So this is the so-called Q+ sensor where a quartz is used, and they measure oscillations of the cantilever of 5 picometers. So very small movements. So again, in atomic force microscopy, you can measure in contact mode, which means you just press your tip to the surface and then you scan it and you watch how this cantilever moves. And this means you're working in this part of the force distance curves. For this, you use small force constant cantilevers, so you want to use a soft cantilever, not to scratch your sample actually. You want to just feel how it looks, right? Sometimes there's some capillary forces, so if you do this in air, of course you have possibly, depending on how high your humidity is, you have some water surface on some water layer on your surface, and this leads to capillary forces that might have to be taken into account for the experiment. Again, there's 2 different ways to do this. One would be in constant height mode. So this is similar to what we saw before with the scanning tunneling microscope. And we just keep that Z piezo constant and just look at the deflection of the tip. So whatever the laser beam reflecting off here is doing is monitored, and this is of course proportional to the surface morphology. And the other option is to go again for feedback. So we feedback to the Z piezo so that the tip bending is always constant. So the cantilever deflection here is constant, and we directly measure the surface topography as the voltage that we apply to the Z piezo. And again, this of course is a bit slower because we need to have this feedback mode. And of course we need to calibrate our Z piezo. So we need to know how much voltage corresponds to which change in Z. But then we get a direct measure of the topography. And of course this is all done by the manufacturers, so there's nothing to do as a user for you. So one general warning, as in all methods, whatever you characterize, there's always a lot of artifacts, there's always a lot of limitations, so always be aware that what you see is not always what you have. So in AFM, this is nicely illustrated here for this one. So if you have two, whatever it is, nanoparticles sitting on your surface, and you have a nicely sharp tip, you can actually measure this. Actually, you still don't know if this nanoparticle is a sphere. You just get this kind of thing. So you still don't know how your surface actually looks. But if you have a tip that's not so sharp, then you might not even get in between the two, and you will just get this kind of shape. So whatever you see here, you don't really know what you have, because normally you also don't exactly know how your tip looks. So the tip is also to some extent an unknown in your measurement. So always critically analyze whatever you measure, and don't jump into conclusions too quickly. Then there is another possibility, and this one is also fairly common actually. It's the non-contact mode. It's also called dynamic mode, and what we do here is we oscillate the cantilever. So as the name says, we are not in contact anymore. We are just above the surface at some distance, and we oscillate the cantilever at its or close to its resonance frequency. Typically use stiffer cantilevers, so they are not as soft as the ones in contact mode, stiffer. And the resonance frequency is somewhere 100 to, let's say, 100 kilohertz to 1 megahertz, depending on what kind of cantilever you use. So this tip oscillates at this frequency. And then the advantages of this mode is that since you're not touching your surface at all, you have a much smaller force interaction. You're measuring in the non-contact part here, in the van der Waals interaction. And that means, first of all, you don't have these lateral forces, and you avoid any contamination of the tip. And in addition, of course, you avoid modifying your sample in case it's a soft sample. The contact mode might actually move particles around or modify a polymer or whatever you want to measure. So here, this is a much softer interaction with your sample, and therefore, in many cases, is preferred. How does it work? So I said you oscillate your cantilever at the resonance frequency, so you just apply to a piezo the right frequency to make this cantilever oscillating, and the frequency, the resonance frequency, is determined by the spring constant of your cantilever and the effective mass of your cantilever. Now if you go closer to your surface, you get this van der Waals interaction, and that means essentially, and it's attractive, so that means your contact, your spring constant effectively gets stiffer. And that makes a change in the resonance frequency, which is normally negative. So your curve shifts to the left. And then there's two different ways to apply this. In air, normally you have an amplitude modulation technique. I will explain this in the next slides. And in vacuum, you cannot use this because your oscillation curve is very sharp. So what the amplitude modulation mode does is you excite, let's say, to one side, let's go here, to one side of the resonance curve, and then as soon as your resonance curve shifts, your amplitude would go down if you excite there. So what you do then is you move back, you move closer until you recuperate your amplitude. This is why it's called amplitude modulation. However, if this curve gets very sharp, because there is no damping due to air in vacuum, so then this is very narrow, and then you will move very quickly out of the resonance. So if there's only a slight shift, you might actually fall to zero amplitude. And that makes it very complicated to control. So in vacuum, people use the frequency modulation technique, which I will also explain in a moment. So here it's the amplitude modulation technique. What I said, you keep the amplitude constant, of the amplitude of oscillation constant, and you just apply a feedback here again to measure your surface topography. And then this is the frequency modulation technique. So here the idea is always to excite in resonance. So you, as soon as your resonance curve shifts, you move your sample tip and you have a phase lock loop normally to detect where your resonance maximum is, and then it always excites on the resonance. So here then you use a different kind of feedback in terms to adjust your tip height. So always exciting on resonance, and then shifting your Z piezo so that you maintain a certain frequency shift with respect to the free resonance. So AFM, this was the simple part. Again, questions so far? Yes, please.
So you mentioned you can control the distance between the tip and the surface of the sample based on these variables, like an interatomic modeling. So this is true if you have like the same material, but if composition changes or you have like a phase segregation, how do you get the feedback to the tip to say here is I have different material?
I think the changes in the van der Waals force between different materials, they are much smaller than what you really, so you might have a small change then, possibly, but I don't think this is really significant compared to what you have in surface topography. So you might make a small mistake there, but I think it's not dramatic. Other questions? Yes?
How do you formulate the tip?
Oosh.
No, I mean, it's a very easy process, or is it...
I think there's different ways. One simple one, which I think is not the one that they use, is we saw in the light management lecture, we saw these inverse pyramids, which you do by KOH etching. So this would be one way to do it. You get but I don't think it's not the way, because the tips here are much sharper than that. You would get a specific angle, and this doesn't comply with it. It's a micro machining technique, and I don't know exactly how it's done.
But you have manufacturers who can buy the tips?
Yes, you buy the tips. Nobody makes the tips themselves. Well, except for you want to have some fancy tip, then you can do it. But yeah, no, you buy this. And one of these cantilevers is on the order of 10 to 30 euros. So depending on, yeah, you can break it and throw it away, or, well, you should not do this too many times, then your supervisor gets angry. But yeah, they are consumable. Yeah. Just like a wafer in 3.5 or whatever. They're a bit more expensive. So one of the powerful things is, so far we only saw the surface structure, right? Not the structure, the morphology, topography. Of course, you can go down to the atomic scale with these methods as well, but that's quite challenging. What's for PV materials, what's much more interesting and common is to combine this atomic force microscopy with other methods. So, simple one is here, scanning force microscopy or atomic force microscopy. But if you use a magnetic tip or a magnetic sample, you can actually do magnetic force microscopy. So you look at magnetic forces. You can do friction force. So you scan and you look at the tilt of your cantilever, which you can also monitor. So then you get a torsion here, and your laser beam would move in this direction. You can use this, for example, to look at different materials. You can do elasticity. There's chemical things, there's electrostatic forces, and I will talk about 3 different ones which are used more or less frequently in photovoltaic materials: scanning capacitance microscopy, conductive atomic force microscopy, and Kelvin probe force microscopy. Let's see how I still have maximum 1 hour, right? So no problem. I will need much less than that. So I start with scanning capacitance microscopy. Obviously, we always look at semiconductors. So capacitance, we heard already actually yesterday in the tutorial. We could actually make capacitance voltage profiles. We were not taught how to do this, but it was there. So capacitance is a quite important property in semiconductors, or useful measurement. So here you want to measure the capacitance between tip and sample, and for this you go into a contact mode. And this provides information about the doping in semiconductors. So what we use here is, in addition to our regular AFM system, we use some capacitance measurement electronics to extract capacitance data. And we do this, so we have here our sample, and we need to have some insulating material here and a conductive tip. So in the end, we have a metal oxide semiconductor junction, which we use to then measure the DC/dV. So we use an AC voltage for this, and we measure the capacitance. So this looks more or less like this. So if I have this tip here on the oxide and I apply a voltage to the tip, I would deplete the charges around this tip position into the semiconductor, or attract the charges depending on what is my majority carrier. And this depletion region leads to a capacitance. So for a semiconductor that is lowly doped, that capacitance change as a function of voltage is very large. And the reason is there's not a lot of charge carriers available, so my depletion region gets quite large. And therefore I get a large capacitance. On the other hand, if I have a highly doped, here in this case P+ material, then for the same, to screen that same voltage here, I have a much narrower depletion region, and therefore my capacitance change is much smaller. So in the microscopy mode, what we do is we use an AC voltage that we apply at some DC bias here. So we oscillate between these two lines, and then we can immediately see that the oscillation in the DC for the highly doped semiconductor is very small, whereas for the lowly doped semiconductor we get much larger variation in the in the capacitance. So that means that if we have a large signal, we have a low doping, and if we have a low signal, we have a high doping. So you can do a calibration curve if you have a sample where you know your doping concentration. So this is like a stack of materials with different dopings that you can then scan. And you see here we have a low signal for high doping here, and then as the doping goes lower to 10 to the 16, so here we have 4 times 10 to the 18, here 10 to the 16, we get more and more and larger DC/dV intensity. So this has been applied, of course, also in solar cells. And I come back to what I said before, polycrystalline, so a quick intermediate introduction, polycrystalline layers. We saw something like this. So it's actually very surprising that these materials get to these high efficiencies, 23%. They have lots of grain boundaries, which normally are defects. We have grain boundaries in all these different layers. But of course, mostly we are interested in the CIGS material itself. So a lot of people have studied the effects and the role of grain boundaries to understand why these materials perform so nicely. And most of the examples I will show are about the grain boundaries, so there's kind of a continuous story. So here it's an example for cat telluride. I have on the next slide also CIGS. So what the people did here, they have, it's the superstrate structure. We also saw this yesterday. So we have glass, TCO, cat sulfide, and cat telluride. Light would come in from here. So here we measure with the tip on the cat telluride, which has a native oxide. So the oxide layer here is just by keeping it in air and having it natively oxidized. And then in the topography, you see these grains. The image quality is not so nice here. Anyway, what you see in the SCM signal, you see these white lines at the position of the grain boundaries. And the color coding here is that white would mean lower doping, and the darker would mean higher p-type doping. So what they explained is that these grain boundaries, there's a band bending. So it's a downward band bending, it's a p-type material, and this means in the grain boundary I have essentially a lower doping. My Fermi level is further away from the valence band in this case. But they also observed here some cases where it turns dark. So just in the middle of the grain boundary there's a very thin dark line, and they interpreted this by an inversion. So here actually we go into a case where at the grain boundary we have an n-type material. So the bends are so far bent down that the type changes and it becomes n-type. So similar things were done also on CIGS. In this case it was molybdenum CIGS cadmium sulfide. So here in these experiments apparently the native oxide was not good enough to make a nice capacitor. So the cat sulfide was used, and the authors also, so you get a fairly similar result. Also again, lower doping at the grain boundaries. But the authors also said that it was not so easy to really quantify the results because the cat sulfide is not really an insulator. It's to some extent semiconducting, and that was complicating the measurements in this study. The next method is conductive atomic force microscopy. Here what you do is you use a conductive tip and you go again into contact mode, but this time you don't want an oxide here. You don't want an insulator, but you want to measure the current that when you apply a voltage between your tip and the back contact, you want to measure the current that flows in your, through your sample. So this is fairly easy, and this is most equipments can actually do this. And you just scan the tip across your surface, and you measure, in addition to the topography, as we already saw before, you just measure the current. So the only thing is you need is a current amplifier in this case. And again, grain boundaries. So this is a copper indium diselenide sample, and what they did again here you can see the topography, and then they observed if they apply a bias voltage. So now you have to apply this bias voltage between tip and sample, a DC1, and in the dark they applied 50 millivolts and 100 millivolts, and they see these larger currents right at the grain boundary. However, if they shine light, then for the small bias, what they observe is that the current turns around. So suddenly the current actually flows in the other direction. And the reason is this is a photocurrent. So this is a solar cell material. So these are photocurrents that we see here, and they are in the same positions in the same grain boundaries. However, when they go to a larger voltage, so 100 millivolts, some of them turn white again, so positive again. So what they interpreted is that there's a band bending at the grain boundaries of about 100 millivolts, so that when the voltage is larger than that, then you get positive currents. You're not getting the photocurrents anymore, dominating, of course. So one of the methods that has been most used is Kelvin probe force microscopy, and this is also what we do in Braga and what I did before in Berlin. And Kelvin probe force microscopy is not related to Kelvin, the temperature, but it's related to Lord Kelvin. And since I realized yesterday that there's a challenge of who can cite the oldest paper, I was working until 12:30 yesterday evening to figure out the oldest paper. So here. So let's see if I get the prize for the oldest paper. So Lord Kelvin measured the contact electricity of metals, and actually in many works you find this paper cited for what is behind Kelvin probe force microscopy. But yesterday evening I read a bit through the paper, and it's actually not in there what is the important part. So what's actually done was a couple of years later, 34 years later, it's the so-called vibrating capacitor method. So Lord Kelvin used two plates and measured then with an electrometer, I guess it was. They use very strange names for all the things. That's the problem with old papers. And they used an electrometer to measure the charge between two different metals. And this goes all back to the definition of contact potential difference, which was a term that was used yesterday by Philip Schultz already. And what then was done based on this, because this is very time consuming. So here it was this so-called vibrating capacitor method. So you still have your two plates with different metals. And then you vibrate one of the electrodes, and you use the displaced charges. So this is in the end a capacitor with a vacuum gap, and you use the displaced charges to measure the contact potential difference between these two materials. And of course in AFM we already vibrate the tip, so that's very nice. But it's not so easy to measure the charges because our tip is very small. So that's not the method we use in Kelvin probe directly, but our sensor here is very sensitive to forces. So what we measure is electrostatic forces. So it's still the vibrating capacitor method, but we measure electrostatic forces. And the way this works is illustrated on this view graph here. So we can assume the sample and the tip let's just go for simplicity just to have them both metallic. And if we have these two completely disconnected, then we also saw yesterday that the vacuum levels are aligned, and we have here Fermi-Level in the sample and Fermi-Level in the tip. Now if we take a wire and we connect the two on the back side, we will get an electron flow from the material with a lower work function to the material with a higher work function until the Fermi levels are at the same level. And at the same time, we develop a step in the local vacuum levels. And we saw a little bit of this yesterday already. So this difference here is called the contact potential difference, and this is equal to the difference in work function between the two materials. So now in Kelvin probe, what we can do is we apply a DC bias just to get the vacuum levels aligned. So one thing what I should mention here is as soon as we have a difference here in local vacuum level, we develop an electrostatic force between the tip and the sample. And of course, this electrostatic force we can detect with our tip. It's a force sensor, right? So when we apply a DC bias that corresponds to the difference in work function, we can align the vacuum levels again, and we get this step here in the Fermi level. So this is the same, but this time it's connected electrically with a bias here. And in this case, again, we don't have any electrostatic force. And in order to do this in our microscope, we also need to apply a AC bias, and this is explained here. So our system in the end looks like this. We have a cantilever, the tip and the sample. We have a DC bias, the AC bias, and then the total voltage between the tip and the sample is the DC bias that we apply minus the contact potential difference plus the AC bias. So we can calculate this assuming that this is a capacitor. It's a strangely shaped capacitor, but that doesn't matter. This strange shape goes into this DC dz. And then the electrostatic force between tip and sample is written here. We just take the voltage squared. So if we plug this in, we get three terms. One is a DC term. One is a term that is the force at the frequency of the AC bias that we apply. And one is a force at double that frequency. This is just by taking out the mathematics, the square. So the DC part actually contributes to the topography. So this is an addition to the topography. And then what's important for Kelvin probe force microscopy is this force at the frequency of the AC bias. So what we do is we apply the AC bias, and then this AC bias will induce an oscillation because there's a force that's written here of the cantilever at this additional frequency that we apply here. It's an electrostatically induced oscillation. And of course we can detect this with our laser system here. So we just take the signal from the photodiode, feed it into a lock-in amplifier that is tuned to that frequency, and we get the amplitude of oscillation at this frequency. And of course that's proportional to the force at this one. So then in the next step we apply a controller, and we use the input for that controller would be that signal. So now we use a controller that reduces this oscillation to zero, which means this force disappears. And this disappears exactly when the DC bias that we apply, this part here, corresponds to the contact potential difference, to the difference in work function between the tip and the sample. So this term becomes zero, the force gets zero, there's no more oscillation at this frequency, and we detect this by using the lock-in on the photo detector here. So the controller adjusts the DC bias to the contact potential difference. Contact potential difference was the difference between sample and tip work function. So if we write this as the work function of the sample, then that equals the work function of the tip plus the DC bias that we apply. You can define this whichever way you want. So it could also be the opposite. But what we do in our lab, we always use it in such a way that the contact potential difference has the same direction as the work function of the sample. So if the contact potential difference increases, then the work function increases. But this is in principle arbitrary. So this is how it works. And now a couple of examples. So initially, just what you can do is you can image a copper gallium diselenide. In this case, it was grown by MOCVD. So there was some textured growth here in the 2 to 0 direction. So there's a mistake. Good. I learned something. No, I knew this before. I just didn't pay attention to this in the slides anymore. But Good. I will do this after the lecture to correct this. So we see this granular structure here. There is a preferential orientation, but then when we look in the work function image, we see this kind of checkerboard pattern. We see places where we have high work function and places where we have low work function. And now the brackets are correct. And what we did is, because we also have a three-dimensional information of our topography. So we know from XRD measurements that the 220 direction is going out of the plane. So we can use the angles that we determine of our facets to that direction and to each other. We used this and compared it to tables for the crystal structure of the copper gallium diselenide, and we were able to index these facets here. Of course, this is an indirect measurement. It's not that we directly measure this, but this is the most probable determination of this facet orientation. And then, I think it's here, we can see that specific facets have specific work functions. So here we have a higher work function for these facets. There are these 112 selenium terminated 112 facets, and lower work function for other facets. So the reason is that, of course, it's why do you get different work functions? On one hand, you can change the doping, but of course that cannot happen in the same grain. We cannot have the same grain with two different facets and different dopings. That's not possible. So the reason is that the electron affinity is changed, and the electron affinity includes the surface dipole, and that surface dipole depends on the atomic termination of the surface. So again, here this is selenium terminated, so selenium is the anion. So here we have a much higher barrier for the electron to come out, so higher work function than in the metal terminated one. However, this work function is measured by forces. So this is very different to what Philipp Schulz was telling yesterday, where he actually takes out electrons from the surface. So it's the same quantity, but it's measured very different. That's very important, and this can also lead to pitfalls in comparing results between different techniques. You have to really go back to understand what you're actually measuring. So normally people say, we measure the work function or the contact potential difference, but you have to consider that you measure this by forces and not by taking an electron out of the surface. So this sometimes explains why the results are different. So it's very important to understand the basics in everything you do. And sometimes it's necessary to not just say, I measure the work function, but you measure it by forces and not by taking an electron out. Okay, coming back to grain boundaries. So here it's the same material. This time it's a chemical vapor deposited growth. And what we did here, we peeled it off. We saw yesterday that there's a molybdenum selenide layer there, and this is easy to peel off. So this is the backside of our copper gallium diselenide. And topography again, so these are smaller grains because this is where the grains nucleate, so you have smaller grains. And then if you image the work function, you see all these dark lines here. And these actually corresponds to the grain boundaries. So it looks like the grain boundaries have a lower work function, which actually is in line with the results that we saw before. There's a band bending at the grain boundaries, and we saw that the work function goes down at the grain boundaries. So this corresponds very well to the other results that were done by scanning capacitance and conductive AFM. So then we can illuminate our sample, and essentially we see the same thing. So that's quite boring, but that's not completely true because there's no scale here on these images in terms of the Z scale, so there's the XY scale. So if I go one slide further, is actually if you take this line scan here, you can see that in the dark we see this kind of behavior, a drop at the grain boundary. So this is the band bending that we saw before, and a larger drop at this other grain boundary here. But under illumination, everything shifts up. So there's a surface band bending, and I think this is on this slide. So if you have a semiconductor, and also yesterday we saw this in the analysis or in the interpretation of the XPS method. So again, here we have the conduction band, the valence band, the Fermi-Level, and the local vacuum level. So normally your surface is not a perfect surface. You have some defects at your surface, and normally these defects lead to a band bending at the surface because you get charges. And this band bending is then also reflected in the local vacuum level. So what you measure is here we measure the distance from the Fermi-level to the local vacuum level at the surface, obviously. And again, we measure this by measuring forces. So you can illuminate your sample, and what happens, you generate charges, and they can they can recharge these defect states. And normally what happens in most of the cases is that the bands get flatter or flat. So in this case, for p-type material, we would expect that the work function actually increases under illumination because this band bending is reduced. So the surface photovoltage gives some information about the surface band bending. Yes?
Just a question. When you illuminate the chip, have you a problem of heating, of dilatation of the chip?
Normally we use lasers normally. So one of the problems, of course, is you have to come under an angle because if you go like this, you have the shadowing of the cantilever. The heating is not a big problem, no. We have done at some point, we assessed by just looking at how the absolute, how the thickness of the sample changes with time if you put the laser on. And there's a little bit of expansion due to the heat, but it's a few degrees Kelvin, so it's not a big deal. But there is some effect if you have to take it into account depending on what you do. Yeah. So because the light goes deep into the surface or deep into the material, we can actually not only measure what happens at the surface, but we can also measure what happens at a PN junction, for example. So again, here, light might be absorbed here. Normally, this would be, for example, a window layer. So light goes through and we absorb here. We generate charges, and then we can also change that band bending at an interface, at a buried interface. So we measure at the surface something that happens at an interface inside the sample. And this is also convoluted with whatever happens or whatever changes at the surface. So it's not easy to separate the two parts, but this surface, the total surface photovoltage that we measure can come from interfaces and from the surface. So now with this small introduction, I will go back. Sorry about that. So if we look again carefully at this, so what we did on one hand is we just subtracted these two images, and then we get the surface photovoltage image. And for this you have to be very sure that the two images are very well aligned. And we see these white lines here. And if we go again to this line scan, if we look carefully, that we see that this drop here is more or less the same, whereas this one here is smaller under illumination than this one. So there's a change in band bending at the grain boundary due to the illumination. And you can see here that this actually appears slightly white. So, sorry, I forgot to say that the surface photovoltage is this contact potential difference under illumination minus that in the dark. So, going back through this. Now, a more up-to-date example. We also heard yesterday that there were technology developments which lead to jumps in the efficiency. So this is the efficiency of CIGS over time, only a part of this big chart with all the other photovoltaic materials. And in 2011, essentially more or less at the same time, ZSW and EMPA introduced alkali fluoride post-deposition treatments. Actually, EMPA developed this for sodium because they used flexible substrates which don't provide sodium as the soda lime glass does. So they had to supply sodium after growing their material. So they developed the post-deposition treatments, but then EMPA and ZSW, instead of only using sodium, they started using potassium and then later other alkali elements. And this post-deposition treatment was adopted fairly quickly by many different labs, and they all had success with this, and eventually they all reached, or many of them reached, efficiencies above 20%. And this was essentially this step here in 2014, very quick sequence of an improvement in efficiency by a few percent. Now it's more than 3% efficiency increase over this due to this alkali treatment. And this was effective in different samples, prepared in different ways, co-evaporation and sequential deposition, We saw this a little bit yesterday already. So when I made this plot, I realized that actually there's a tendency here that initially was sodium, then people started potassium, then rubidium, and then even the most recent records are with cesium. So it appears like there's a dependence on the alkali element, and that means if you go down in the table, so the heavier the alkali gets, the higher the efficiency. So the question is this really true, or is this just because people spend more time on optimizing specific processes? And the other question that we want to ask is, are the grain boundaries at all relevant for this? So there's many different people, lots of work on how this works. There's surface phases that have been identified, changes in doping concentration. So there's a lot of different effects happening due to this alkali treatments. And we wanted to see if there's anything happening at the grain boundaries, because there were observations by atom probe tomography and electron microscopy, and maybe tomorrow we will hear some of this from Daniel Aboraz, I'm not sure. So it is fairly well known that alkalis tend to accumulate at grain boundaries. So we wanted to see if we can see something in our method. So this was part of a European project where we collaborated with ZSW, so we had access to very good samples. And again, we imaged the topography, we image our work function image, and now you can already see here our grain boundaries suddenly are bright. So instead of going down, now we actually see an upward change of the contact potential difference. So normally what we do here is, in order to not get confused by this image, we look only at this one and we identify our grain boundaries. We decide which ones we want to analyze. And then we take this line profile across the grain boundary in our contact potential difference. So we get a bunch of these line profiles here, and we do this in different macroscopically different spots on the surface. And we analyze this by looking at the value on the grains, and then we take the difference to the value at the grain boundary. So this grain boundary here would have a positive change of the contact potential difference of 320 millivolts. That's quite sizable. And in this study, we extracted actually then 20 to 60 profiles in each of the samples, and we plot then the CPD difference for all of these 3 different treatments. So overall in this study, we analyzed more than 240 grain boundaries, which was a lot of work. And what we find is, for potassium treated, we see a lot of grain boundaries that do not change at all. So this is why we use the topography to identify the grain boundaries, because if we only would use the CPD image, we would not see, of course, if there's a grain boundary that doesn't change, it would be invisible. So we have this part, then we have a few grain boundaries that show downward change in potential, and a lot of them upward. For the rubidium one, we only see upward and neutral ones, no change, but the change is also much smaller. And then for the cesium, again, we see some more with larger changes, but again, no negative ones. So what we know, of course, is here we have a higher work function at the grain boundary, so this corresponds to an electron barrier. So if I have a transport across the grain boundary, this would be a barrier for electron transport. Neutral one doesn't change anything. And for the downward one, we have a hole barrier. So now we talk more about electron and hole barriers in this case. So we statistically analyze this, and we see we have here about half of the grain boundaries in all 3 alkali treatments are electron barriers. Here we have some hole barriers, and then we have also a fairly large fraction neutral ones. So more or less 50-50 here, and here we have a couple of 10%, 12% of hole barriers. We did this also for a coating with a zinc oxysulfide. This is not important for now. So then we had another team in the project consortium from the University of Parma, and they're doing device simulations. So we teamed up with them, and we asked them to simulate grain boundaries. So they have a grain boundary here, and then they have all the different device parameters. So this is something that we saw yesterday evening. But of course, these simulations are 3-dimensional simulations, so you cannot do this with the SCUPs, as we learned yesterday, but you have to use more elaborate methods. And The nice thing in the project, they extracted by different measurements all the parameters for the real material that was grown in the study. So there's a baseline result. It's this one here. All these parameters are really taken from an experiment. And then a grain boundary with a 1 nanometer thickness was included, and fixed charges were placed at the grain boundary, and the polarity was changed. And then we looked at what happens for hole and electron barriers. And this is the change at the grain boundary, the potential change at the grain boundary for the different parameters. And you see immediately if there's an electron barrier, that doesn't affect the device properties at all. Only hole barriers will affect the device properties. So then we can look at IV curves from the samples we looked. So some parts of these samples were finished into devices, and we looked at the IV characteristics. And we can see in the current there's minor change, but there's a huge change in the voltage. So the potassium one was not working very well, actually. So the potassium has the potential to be actually much better than that. But this very sample was not very good. And then here we have rubidium and cesium. And you can actually see here the best efficiency in this case was the rubidium one, not the cesium one. So now what we can use the information from our simulations. So we can look at the open circuit voltage, and we know what is the gap, and we can calculate the loss in open circuit voltage for each of these band bendings here. And this is plotted here as this line. And then we also know for our very samples where they are, how much open circuit loss we have with respect to the band gap. And we know from our images the average CPD change at the grain boundaries. And we get these plots which follow more or less the trend of this line, but everything is above this line. So there's more processes that lead to loss in the open circuit voltage. It's not only the grain boundaries, obviously. Whereas here we only consider what happens due to the grain boundaries. And then we can look in the literature and find, in some cases, we actually find studies with KPFM that looked at these changes here. But in many cases, you don't find a corresponding device. So there's only a couple of papers where there was actually device efficiencies reported, and they also come to lie more or less on this line. So there's a fairly decent agreement between the experimental results and this, in general, this behavior. But of course, most of the data points, or all of the data points, are above this line because there's other loss mechanisms, of course, interfaces and so on. One thing that I mentioned slightly is that actually the potassium fluoride treated sample is below what it can actually perform, so that one should actually have a much lower open circuit loss, voltage loss. And this tells us that you need to have actually a fairly good fine-tuning of the conditions of your alkali fluoride treatment in combination with a CIGS surface. So it's not just simply doing alkali fluoride evaporating on top, but you have to optimize the process for your absorber. And this one was not completely optimized. But it tells us that if we have large band bending at the grain boundaries in terms of an electron barrier, then we have a loss in our device. So we try to go one step further, and we come back now to this surface photovoltage. So we also illuminated and we studied again the grain boundaries. So essentially what we have is the cases here where we have upwards or a higher work function at the grain boundary, a lower work function at the grain boundary. And this can be due to band bending, but this could also be due to a different material. I mentioned before that the alkalis tend to sit at the grain boundaries. So there might be some alkali phase formed at the grain boundaries. So we might also have a different phase at the grain boundary. So then we looked at what happens if we illuminate the sample, and then we can analyze this according to different situations. Like if we have the CPD going up, the surface photovoltage could be down, so that means we get a lowering of this upwards band bending here, but there could also be no surface photovoltage or an upwards surface photovoltage, so that would mean that the barrier gets higher under illumination. So we analyzed all of these cases, and in the end, we know here we have in a pure band-bending situation, in this case, for example, we would have positive charges sitting at the grain boundary, and then under illumination, the band bending would reduce because these fixed positive charges would be shielded. So in this case, we have positive trapped charge. It's a whole barrier, but then under illumination, the normal situation would be that we get a reduction in this band bending, and then we can say we have positive charges sitting there. So in the end, we use this analysis to define if we have negative charges, positive charges, or if our grain boundaries are uncharged. And if we look now at this, this is the distribution of values, CPD plus minus. So we look just at the outside ring. And we see that here in the KF case, we have a lot of grain boundaries that are negatively charged, a few uncharged, and also a lot positively charged. If we look at the rubidium one, the negatively charged part is smaller. We have uncharged and positively charged. And in the cesium one, we have a lot of uncharged ones, a few negatively and a few positively charged ones. So if we plot these fractions of grain boundaries as a function of charge, so we have the negative charges, they are going down as we increase the weight of our alkali element. The uncharged increased, and also the positive charged ones go down. But the major point is here the uncharged increase. So how can we understand this? Uncharged means we see some modification due to a different material at the grain boundary, for example. So also part of this consortium was a group from Finland, from Aalto University, and they simulated by DFT simulation the stability range of a Kali indium selenide material. So in the phase diagram, we also heard yesterday, phase diagrams are really messy. So here, if we look at this sodium indium selenide phase, we have here the chemical potential for sodium, here for indium, and then depending on where you vary, you get sodium selenide, selenium, indium selenide, different composition of indium selenide. But this is the one that we are interested in now. So they calculated this stability range of the sodium indium diselenide phase. And if we now go to potassium indium, we see that stability range is actually larger. So the axes don't change here. So rubidium is even larger and cesium is even larger. So if I plot these four differences here, we can see that the heavier the alkali element, actually the more range of stability I get for this phase. So that means, depending on where my chemical potentials are, it's the alkali indium selenide phase gets more and more stable the heavier my alkali element is. And at the same time, they also said that the band gaps of this phase are quite large. So that can explain a passivation effect due to a conduction and valence band offset. So that's a bit the model that was already there partially before, which we extended a little bit. So before alkali treatment, you have a lot of sodium that comes from the glass in these samples. But then when you're doing the alkali fluoride PDT, this sodium is displaced by the heavier alkali into the grains, where it then leads, and we saw this also yesterday, to a higher doping level. So this part explains why the doping level changes due to the heavy alkali treatment. And then after the alkali fluoride PDT, we get the formation of these alkali indium selenide phases. They are not complete. The concentration of the alkali elements is not large enough to make a full phase there, but there is some contribution of this wide band gap phase sitting at the grain boundary. So since it's also perovskites are very famous materials, I also had to include a perovskite study here. So this is not by us, by other people. So I'm not only presenting our own results, but also other people's results. So what's come up in the more recent years is time-dependent studies of Kelvin probe force microscopy. And this is one that is in real time. So here it's just in a range of seconds. But there's also methods where you can use this to measure really in much faster timescales, in micro and nanosecond timescale. So here it's a study on a perovskite material. This is the perovskite surface. So they measured the topography with Kelvin probe force microscopy, and it's a special mode of Kelvin probe force microscopy that allows to scan very fast. So normally you take, let's say, half an hour to an hour for one image. Due to the method they used, they can measure one image in 16 seconds. And this allows, of course, then to look at dynamics in the sample on that time scale. So they get this kind of pattern in the CPD image, and then they only looked at what happens here. So initially they measured in the dark, which is this image here, but then they illuminated for some time, and then they switch off the illumination. And then what they see is that after switching off the illumination, even after 16 seconds, you don't get the same thing. But then as they wait longer and longer, they go back to this same state. So they analyze this by histograms. So we start here in the bottom. This is the dark image. Then under illumination, that's between or during this time here, they have light on, so we get quite a significant change in the CPD. And then when you switch off the light, you don't come back to this one, you get this shape. And then with time, and this is the final image here, they go back to this. And what they explained is that you have, of course, and I'm not an expert on perovskites, but if you have questions, there's one there, at least one. So what they explained is that the changes that happen very quickly is electronic changes, whereas the changes that happen on this time scale of tens and hundreds of seconds is ionic movements. So this causes this change. Of course, this is an indirect interpretation. They cannot completely prove that, but they can correlate this to other timescales or to timescales measured in other experiments. So should I stop here? Since Suzanne only used 1.5 hours, I have a bonus track, but I'm not sure if we should or should not do it.
Maybe we can take the few minutes we have for questions.
Sure. Yeah. So there's some literature. If you have tons of questions, read the books. The short questions we can answer now.
Thank you very much.
I see in the literature that some people they use KPSF, not the local VOC to is it like a shortcut?
Yeah, this is a bit controversial. There's one paper, I think that was the first one that claimed that, and I'm not very convinced by the method because there's kind of an arbitrary parameter that they adjust to get the open circuit voltage. And there was a recent thing that I saw last year at the MRS meeting, which I think is much more reasonable way to do this. They actually they illuminate the sample, and they did this, I think, on a cadmium telluride, if I remember correctly, so they can illuminate from the backside. So one of the problems, of course, if you have your tip and you want to illuminate from the front side, you normally use a laser, and it's never sure how much intensity actually gets to the point where you're measuring. And then the same as you explained yesterday, there's charge carrier diffusion if you don't illuminate the whole sample. So it's a very tricky situation. Then, of course, the sharp tip also does reflections and so on. So it's not easy to know what's your light intensity. So it's much easier to illuminate from the back if you have a transparent solar cell, like a super straight solar cell, and you can measure on cap telluride. And what they did, I think they illuminated with one sun, and they adjusted the voltage. They used a controller on the voltage to get to zero current. So they were measuring in contact, measuring currents, and then used a controller to apply the voltage that would nullify the current. And then they said they measure directly the open circuit voltage from grain to grain. So this is much more convincing to me than the other method. And even, I think, in that last paper, they claim to some extent that they measure the open circuit voltage, which, again, I only put this in last night because I felt obliged to show some perovskites. But yeah, it's a tricky business.
Yeah, maybe I also wanted to ask some questions on the literature on the paper from Marina Group, I guess.
Yes.
So they still measuring the capacitance, right, and changing the capacitance.
Mhm.
I think it can be, let's say, measure open circuit voltage, but if there are some interface effects, and just as you described it for the lamp, and you have no correct interfaces, you
Right.
can flatten it out by illumination, but not necessarily convert it to a voltage. I'm not so certain if this has been captured here correctly, but to look at the different time scales and different differentiating between processes, I think is important.
Right, that's why I took this part out of the paper and not the more difficult one. Yeah. So for me, it's always a question. I mean, we heard yesterday from Laurent about the quasi-Fermi-level splitting. But of course, if you make a device with an open circuit voltage, you also get all the trouble with the contacts, right? So your open circuit voltage normally doesn't match that one. So in this sense, if you just measure on the absorber, as is claimed sometimes, you cannot measure the open circuit voltage because you don't have the contact there. Or you have a contact which is your tip, which again is different from a device. So it's not as straightforward for sure.
Other questions? Yes. Yeah, I have a question on the CIGS result that you show with this alkali selenite that are the grain boundaries. You mentioned you have a large band gap.
Yeah.
And so of course these phases are known, but the thing is that I'm not sure how stable they are to oxidation. And so, I mean, would they, and also about the conductivity. I know they have been reported, and so in principle they can be beneficial, but also unless they block the current also between the grains, or they can cause some other problems. So do you know about the stability or conductivity of these layers?
The stability, I don't know, but normally, since they're sitting in the grain boundaries, so oxygen would have to come there, and we know that most people try to do the cat sulfide as fast as possible. So this might avoid any oxidation.
Are they soluble?
This I don't know. This I don't know.
You know the band alignment of this white band that comes in that one of the CIG?
No, not really. So I think these are, as you say, they are not stable, not very stable phases. So if you try to synthesize them, it's not so easy to measure them. So in this sense, but we are not claiming that we have really a phase from the bottom to the top. Yeah. So there might be some patches where you have a beneficial effect due to that. Yeah.
Maybe one short question from me. You showed in one of the first slides a method to measuring doping using these MOS structures.
Yeah.
And I saw that your signal was kind of saturating at Q4 10 to the 18 per millimeter. Is this something specific for that particular material measurement, or there is some problems in measuring higher doping levels?
I don't know. No, I wouldn't know. Maybe this was just the reference sample they were fabricating. I think this was a stacked silicon doping profile for these calibrations. And I don't know.
Okay.
I don't know. We should have a question from a student, I think, no? Yes.
I have a question on organic bulk heterojunction. So conventionally, when they try to image the domains, they use a very thin layer and then do STM. But then I don't think the same domains are captured when you make a thicker layer for a solar cell absorber. So is there any way of doing it with an AFM and a thick layer of absorber?
As far as I can tell, I mean, at least for KPFM, I think most of the people use the regular thickness for imaging bulk heterojunction materials. And there has been quite some work done on this. But for STM, maybe it's because the materials are not as conductive, and that's why they use the thinner ones. But I don't know much about these materials, so I'm afraid I cannot answer your question. But I think in KPFM it has been done on regular thicknesses.
My only issue is as the thickness increases, your processing conditions change, and then I don't know if the same domain sizes are captured.
Yeah. Well, That's good critical thinking. No, but I don't think I can help you. Yeah.
Sure, last question.
Come on, another student.
Oh, okay.
This one question is probably an order of mine. When you showed the data with 250 centigrade, how much time did it take to make it?
So we were fortunate we had an Erasmus exchange student who was supposed he was supposed to do measurements, but the AFM broke. So here you have some data. And he spent a lot of time. So it took long time. So this whole analysis story took maybe a year and a half to analyze and finish and interpret and look again at the data and so on. So this was quite time consuming. But it would be nice to do this in a more automatized way. So my next proposal will have big data in it.